And thank you to the KGRC and Vera and all the people involved, I'm sure, that for organizing this meeting. I know it's a lot of work to organize a meeting, or rather I know that it through David, but it's wonderful that you're doing it, and it's wonderful to be in Vienna. I'm going to do a Blackboard talk, and essentially the whole talk will be showing you a proof which is of the following theorem. As you know, I've been for several years now interested in various problems surrounding MAD families, maximal almost disjoint families, and their definability. And this theorem here is the latest one to come out of these efforts, and it is joint with David Schridesser. So it's from earlier this year, so 18. It simply says that assume the following. Well, we're going to work in set F plus dependent choice plus all sets are completely Ramsey. Completely Ramsey. So what I mean by this is first that if you look at the infinite subsets of omega in the Allen-Tuck topology, you might instead formulate this by saying that every subset of the infinite subsets of omega has the Baire property in the Allen-Tuck topology. And then, so we have dependent choice, which we'll need in a few places. And finally, we need uniformization. I'm just going to write uniformization here and then say that we need actually only something a little weaker, namely, so by uniformization, you probably guessed that if you have some, what I mean by this is if you have some relation, we're going to be interested in relations between infinite subsets of omega and points in a Polish space Y, so this is a Polish space, then if I have such a set and it holds that for all x there exists a Y, sorry, for all x in the domain of this, something to, oh, wow, that is high tech. This is dried up like the things in the museum exhibit in this building. So for all x, now I can't write on this, sorry. So for all x in, oh, and now this is also wet. So for all x not in bracket omega to the omega, so for all things in the domain of this relation, there exists some y in y such that x comma y is in Q. If I have such a relation and this holds, then there is a function theta omega to the omega into y such that for all x in bracket omega to the omega, it holds that x comma theta of x is in Q. So that's what I mean by uniformization. And now it's actually very, perhaps fortunate, well, anyhow, there's this gap here, and that's fortunate because, as I said, I could do with something weaker than uniformization, but maybe I'll just put this here, and what that means is that I can uniformize on an Allen-Tuck co-meager set. That's actually what I need. I don't need outright uniformization. So assume all of these things. What's the conclusion, or what's going on here? Then there are no infinite MAD families. So MAD meaning almost disjoint, maximal almost disjoint families, so families of infinite subsets of omega, such that the intersection of any two elements in the family is finite. Everyone knows what a mad family is? Good. So then there are no infinite mad families, and this, this is, I had a proof a few years ago that there are no mad families in Solovey's model. That is implied by this theorem because all of these things I've just said hold in Solovey's model. All the assumptions here hold in Solovey's model, certainly at least the version of uniformization that I really need. Other theorems, recent theorems of Itai-Niemann and Sack-Norwood had results about what happens to projective mad families under PD, and again, they are implied by this theorem. So now, just sort of to clear something up, I gave a talk about this in Lausanne, and so what happened was I gave that talk, and I had just come up with the proof, and I typed that proof up, and a few days later, I ran into David, and David then told me, I've proven this thing, and I was like, I have too. So it's not really a surprise, because we have this big project together with, so Schroeder plus my student, Karen Hoga. We have this long-going project of studying mad families relative to other definable ideals in omega, so other than Finn, right? So here we're doing classical mad families, so we're using Finn as the finite ideal of finite sets to say what it means for an intersection to be small. But you could use a different ideal, and we have this long-term project that hopefully will one day produce a long paper. And then the ideas in this proof that I will now show you very much come from this joint work. So, and what is sort of the central theme that you should be looking out for as I now start to show you this proof? The central theme is that we will be attaching certain, so we will take some definable, we'll take some mad family, we'll assume these things, we'll take some almost disjoint family, we want to show it's not maximal, and then we will attach certain objects to this almost disjoint family, and these attachments of objects are E0 invariant. So what is E0? Well, it is the best friend of descriptive set theorists in the last few decades. This namely, let's, in our context, say that E0 is the following, that it is the equivalence relation that X is E0 equivalent to Y if and only if the symmetric difference, so X and Y here, are going to be, well, let's just say that they're subsets of omega, that the symmetric difference between them is finite. So that is, of course, that's an equivalence relation. I'm sure you've seen it many, many times. But the key thing that's used in the proof is that certain things we attach to this almost disjoint family are E0 invariant. And this E0 invariance is then used together with this all sets are completely Ramsey to show that these things that are attached must actually be constant on fairly large sets. And once they become constant, you ramble into a contradiction. So that's, anyhow. So I'll start in the proof now, but this is the thing to be keeping an eye on, this E0 invariance. And just tying up this knot with this joint work with David Schroeder and Karen Hoga, the thing is that it's the same type of invariance, E0 invariance, or other types of invariance under equivalence relations, that's the driving force in the proofs here as well. So it's not so surprising that when I came up with this proof, David at the same time came up with the same proof, because we were really thinking about these E0 invariance ideas. Good, so that was good. Well, one thing that we will need in the proof of this theorem again and again is the following proposition. So, so again, I'll work in set F plus DC plus all sets of Ramsey. I'll abbreviate that now to just Ramsey. And then the proposition I need is that if F on bracket omega to the omega into y, and this is Polish, is given, or let's put it this way, let F be given, then there is some infinite subset of omega such that if I take and restrict F to the infinite subset of that infinite subset, that this is continuous. With respect to the Polish topology. So of course you have a Polish topology on bracket omega to the omega. Just you can identify that with increasing functions from omega to omega, and then it's easy to see that gives you a way of identifying bracket omega to the omega with bare space. So of course you could do the same with this thing here anyhow. So you have so there's natural Polish topology. This. Now, of course, again, looking forward in the proof, we will have certain functions that are attaching to infinite subsets of omega, some other thing in a Polish space, and they will turn out to be E0 invariant. And the punchline again and again is going to be, well, it's continuous on some, well, we can restrict the function to some, to infinite subsets of some infinite set, capital A. And if it's also E0 invariant and continuous, it's going to be constant. So this is what you're looking for. The E0 invariance and this proposition together is going to give us that certain functions become constant on and the infinite subsets of some given infinite set. All right, so here's what we're going to do. I'm going to start in the proof now. Oh, yeah. So I'm out of practice with this very thorough and Austrian way of wiping down the board. I used to be very good at that. But the trick is to have sort of comments or remarks or jokes or something like that that you can make about what you're doing. Now I need this. Is that here? Oh, it's here. There's also a bucket so that I can clean the whole room when I'm done. And the floor really needs it. I don't know who did this. And then if you don't use enough water, I think I managed to use enough water, you're really not achieving much by making the blackboard wet. You're making life worse for yourself. But I think I succeeded. Oh, there we go. Good. So here's what we will do. Well, I'll take, so let script A be an infinite. So this is the proof. The proof is now starting. Proof. Let A be an infinite almost disjoint family. Almost disjoint, AD, family. Now, because it's infinite and I'm assuming DC, it's Dedekind infinite, so I can take an infinite injective sequence from this. So let xn and omega be an injective enumeration of a subset of script A. And now I've taken this, so this is in itself, I mean, this is in itself some countable subfamily of script A that I've taken out and enumerated, and I will make the additional assumption, assume additionally that if m is different from n, then xn intersected with, xm is actually empty and not just finite. And of course, I can modify my family on these infinitely many, so countably many elements simply by replacing xn without the things that came before it. So otherwise replace xn with xn. So you could call it xn prime or something like that, which is just xn without the union of what came before it. So xi less than n. So this step is not this is not strictly needed, but it makes the following drawing look much nicer. And the drawing is the following, that here I will draw these lines, infinitely many of them. And I'm imagining that's what is up here in the corner of the blackboard is a picture of, here is omega. So I don't know where to write omega. I'll write it here, because that corner of the blackboard is now omega. And I have countably many disjoint subsets of omega, namely the xn, and so what is here is x0. Maybe I should make a better drawing there, not perhaps lines, but I'll make a better drawing. So this is x0, it's some subset. Here is x1, here is x2, and it keeps going, and here is xn, and it keeps going. And of course, you have these subsets here, and they are infinite subsets of omega, which is this corner of, so that's what I have right now. Now, the next thing I'm going to do is I'm going to, I guess, do two things. First of all, I'm going to define script A prime to be the set, the set A without these xn, and we will assume that A prime is non-empty. And that's, of course, because if I was actually A, then we could easily see that it is not maximal. So we will assume that taking away the special elements I've enumerated will leave something behind, and which we call A prime. So, this is, we'll assume that it's non-empty. And now I have a bit of notation which I think some people have said is frustrating, but I have stuck with it in order to keep frustrating these people. So what I will do is that, so every time for z in bracket omega to the omega, let z hat from omega to omega be the increasing so now I have to move over there. I have no jokes prepared, so I just have to, but fortunately I'm very, very fast. Extremely fast, and increasing enumeration the increasing enumeration of Z. Now, I mean, so Z is an infinite subset of omega, and of course there's an increasing enumeration of that. So really strictly increasing injective enumeration. So that will be Z hat. Now, I'll define more notation, but this is really the key one. Z tilde, so again, Z is an infinite subset of omega. Z tilde is going to be, well, x hat, Z hat n, this is probably the part people don't like too much. Z hat n plus 1. So now but this is why I've made this brilliant drawing of omega with subsets. Because here, inside of x0, I have the elements of x0, which I will draw like that. And this element here, the smallest one, is x hat 0 of 0. And the element here would be x, oh, sorry, need more space. This here would be x hat 0, so I'm still enumerating x0, so x hat 0 of 1. And this here would be x hat 0 of 2, and so forth. And here, the same thing. So this here would be x1 hat of 0, and that here would be x hat 1, or x1 hat, rather, of 1, and so forth. So this is, this is what this notation is doing. And what is it that I'm doing here? Well, I have my Z, and I'm forming a new subset of omega by taking what? Well, Z is going to tell me to go out to some point, right? So let's take Z hat of 0. So that's the first element of Z. So it tells me to go out to that set and then find the Z hat of n plus 1 element of that. And so forth. Right, what would happen? I would first look at Z hat of 0, which is 1. So Z hat of 0 is 1. And so x hat of Z hat of 0 of Z hat of, well, now n plus 1, so 0, so of 1. What's that? Well, so x hat, so Z hat of 0 is 1. So this is just x hat of 1. So we are in this set here. And then I look at Z hat of 1, but that is the second element in Z, so that is 2. So this is actually this is just x hat of 1, so x hat 1 of 2, which is, I hope, the third element of x1, this one. And you could now go on and say, compute what is x hat of Z of 1 of Z of 2. And now you can see we'll get Z of 1 is 2. And you will, so we are over in this set. And then you will do 4. And so you'll end up, I guess, taking the fifth element. Is that right? So you can see but anyhow, so now this has been explained in an example. So, and now comes and perhaps to say something, if you now imagine, and this is what you really should be imagining, because in a minute I will be looking at a genericity argument where I'm attaching something to Z tilde. And what you should really keep in mind is that if you took Z to be a subset of omega of extremely low density in some way, like that has enormous gaps in it, what is happening here is that you are both getting something, the set you're defining, the set tilde, is both going to have these enormous gaps along here, but it's also going to go up. The element it picks in those things where it will pick something from is also going to go up very fast. So that is what is going to happen. And I think, in some sense, this is crucial for the proof, that you have, in some sense, this rapid growth in both directions. I believe that is crucial for the proof. Okay, so the main claim is the following. There is Z in bracket omega to the omega, so an infinite subset of omega, such that for all y in our almost disjoint family A without the elements that have been the special elements, the xn's, for all there is a Z, so that for all y in A prime, we have that Z tilde intersected with y is finite. And that will do the trick, because if you think about it, this construction of Z tilde will intersect each of these x0, x1, x2, and so on in at most one point. So if I'm only hitting the things that are not enumerated in finitely many points, everything from the coming in. Such that theta of Z intersected with Z tilde is infinite for all Z. Did I say for all over there? No, it's for all Z. So we get that by uniformization. And if you look into the details of the proof, we really only need to uniformize on a Ramsey co-null set or an Ellen-Tuck co-null set. Okay, so now I'm going to use the proposition that was there. And the proposition said that assuming all sets are Ramsey and dependent choice, once I have a function from bracket omega to the omega into a Pauli space, then I can find an infinite subset of omega on which that function becomes continuous. So let W be an infinite. I had promised myself to write a really good W in this talk. I think that's a better W, because otherwise people start thinking that my W looks like omega, which is why I chose W. This is one of these bad choices that I might sometimes make. But of course, it's natural, right? I don't want to look at all of omega. I want to look at an infinite set and never think about the rest of omega again. So I called it W. It looks like omega. But anyhow, but we let W be an infinite subset of omega such that theta restricted to good W, omega is, so the infinite subsets of good W, omega is continuous. And then, of course, if you take the range of that, now it's a continuous function on a continuous with respect to the Polish topology, the range of this is going to be an analytic subset of script A, in fact, of script A prime. And now we're getting a little bit of definability in here, and that's exactly what we are looking for. So is such that this is continuous. So let what did I call it here in my notes? I called it I called it A tilde. Script A tilde is the range of theta restricted to good W omega. So this is analytic, so let T be a tree on 2 cross omega such that the projection of T is equal to a script A tilde, this analytic subset of script A prime. So I may as well write that this is a subset of script A prime. Very good. So here we go. Okay, so here comes the E0 invariance bit. So for each Z, well, I'm really only going to care about infinite subset of my good W, but we can make the definition for every infinite subset of omega. So for each Z in infinite subset of omega, let T Z be equal to the T in T such that there exists some Y in the projection of TT, and I'll explain my notation in a second. There exists a Y in the projection of TT such that Y the T in T, that T is giving us the analytic subset of script A prime. So I'm looking at the nodes in that tree so that there exists an Y in the projection of the local tree here. I'll write down the definition in a second. Just the Y says that Y intersected with Z is infinite. And just to make my notation clear, so T, what I'm writing as T sub T right now, I mean the T, so the S in T, so that S is compatible with T in the ordering of the tree. So later on, I will definitely only be interested in this definition for Z tilde. But for the minute, I'm just defining it for a general subset of actually, you're right. In my notes, I could define it in general, but in my notes, I've decided to do what Sai is suggesting, that we speed ahead to what we're really interested in. We're really interested in the ability of an element from this part of script A tilde to hit Z tilde infinitely. So that's what we'll look at. Good. Now, what we have here, if you think about it, is a map. Oh, good. Now I have something to say while I wipe down the board. So I'll be very slow. So what we have now is a map from Z to T set. So from a subset, an infinite subset. This isn't very wet anymore. So now what we have is a map, a function from Z to T set, which, if you look at it for a moment, is at least sigma of sigma 1, 1 measurable. So, so I'll write that down once I've. But the other thing about this map is that it is E0 invariant. So we'll get. So the map Z maps to TZ is sigma of sigma 1, 1 measurable and E0 invariant, i.e. if Z symmetric difference Z prime is finite, then TZ is equal to TZ prime. So, because of this, that it is sigma of sigma 1, 1 measurable, sort of a remark about the definition of this, we don't really need it because we're assuming all sets are Ramsey, but because it's E0 invariant, we can now restrict ourselves to a subset where this map, subset of omega. Yes?
I mean, I'm confused. If Z and Z prime, for example, and then this Z hat and Z prime can be very different. No? So how do you know that they are TZ is equal to TZ prime?
No, I think it's fine. So if, because I'm just enumerating, right? So I'm just going out. Sorry.
But if you just delete the first point.
Yes.
So you're starting, so what you do, you're taking the first point is that they take the x with that index, and then take the next point of that point of that. I mean, if you just delete the first point, everything gets shifted. You don't get range, you don't. That is maybe very wrong. Right? You probably don't need to go.
So yeah, so if I.
You didn't write the tilde, I wrote the tilde. Right?
Yeah, so it's certainly, yeah. It's certainly true if I say this. But that temporarily at least gets us out of trouble, I guess. So if I have, let's see, if I have this subset and so maybe I didn't exactly mean what I wrote. So because I want to simply just take, I deleted my picture. Yeah, I probably don't mean what I wrote. What I have, so, sorry? Yeah, so,
if you're in the range of this enumeration,
yeah.
It doesn't matter what index you get assigned to. At some point, it will be in the range of the point following the also.
So So I'm taking.
In the end where this gets enumerated, you just
yeah. So if they have, let's say that 3, or let's say that 2 is, oh, that's not very good. So let's say that 1 is in Z. Then I will go in here to this, so that I have my x0 and my x1. And I will take, you know, whatever comes next here. Like, so I will now, let's say that this is 1 is equal to Z hat of 0. And let's say that Z hat of 1 is equal to 3, which is in Z, or something like that. So what will this do? It will take, inside of x1, it will take it will take the third, or fourth point, I guess, the fourth point here. So that's what we'll take and put in there. And now I will crawl out and, so if Z from a certain point on, if Z and Z prime from a certain point on are identical, then you're always picking out things in the same here, and you will make the same sort of determination of which point inside of this you will take. So I think it works. Yeah.
The point is, there's a way of writing this down where you don't care about the enumeration, just points follow.
Yes, yeah. So, but thank you. Yeah, I survived because, so thank you for asking that question. It works. So it is E0 invariant. We've come down on that side, and as I said, okay, so this map here, we don't really need this, but it's nice to know that actually it's sigma of sigma 1, 1 measurable if you care about such things. And so by our proposition, by the proposition I wrote down in the beginning, we can find some, and now I called it, I've already made it continuous. So I can, and it is E0 invariant on this, so actually I don't need to write everything I'm writing. What I mean to write is, so it's continuous, it's E0 invariant, and it's continuous on my good W. So Z maps to TZ is constant I made my theta. Oh, yeah, no, I can arrange that. It doesn't have to be. I guess I made this theta continuous in order to get an analytic set. That was the point. But now I've just move on to, oh, there it is. I'm sorry. So now I can find some good W0 in the infinite subsets of W such that Z maps to TZ is constant on bracket good W0 omega. Right? I have this. I have a map. It is E0 invariant. I can make the map continuous on some subset of this, and it is E0 invariant, so it must be constant on that. So I can certainly do that. Good. So now, also note that by our assumption, theta of z is always, of course, an element of script a prime, which meets our z tilde in infinitely many points. So note that t is that empty is in tz tz for all z, since there is some, let's put it this way, since theta of z intersected with z tilde is infinite by assumption, right? So there really is something in this analytic set A tilde which meets z tilde infinitely, which is the criteria for that empty, the initial node of the tree is in there. So Tz is different from the empty tree. It's a non-empty tree. 5 minutes, oh gosh. So I blame the board washing. And the board washing blames me. So let me wrap it up here. What's the steps? So now, first, it's too bad I don't have a little more time, but okay, so the other one is better, but I keep losing track of it. So subclaim 1. I've made this constant. So let me, so this is always in Tz, and it's constant. This function z maps to Tz is constant on omega 0. Let T tilde be such that theta z is equal to T tilde for all z in nice W0 omega. So that's the constant that tree is. And then the subclaim 1 is the following, that the projection of T tilde, this subtree of T, that this has at most 1 point. Now, this argument, in fact, I don't feel so bad about skipping this argument, because this is exactly the style of argument that, if you're familiar with my paper on nomad families and solid-base model, that you do this thing where you crawl out through the tree and say, suppose that there are 2 different directions in the tree. Now, and you keep on crawling out, then at some point you get to 2 nodes in the tree where everything that's built beyond those 2 nodes do not intersect any further. They may intersect previously, but you have these 2 incompatible nodes where at some point you don't see any more intersections. And this argument has been used again and again, but was first used in my nomad family and solid-base paper. So I don't feel so bad about skipping this, because it's exactly that. If they split, then extend, build something, contradiction. So now we get to that this here has at most 1 point, and so the subclaim 2 is, in fact, that the projection of T tilde is empty. So proof by subclaim 1, there is, if not, then there is y projection y in what I've called A tilde, or A prime, doesn't matter, y, such that this projection is just that point. Projection of T tilde is just that one point. But now we come to the punchline of the definition of this set tilde, because now I can just let Z be a subset of my good omega 0, omega, so an infinite set there, such that it holds that, what I'm supposed to write. So look, I have again my x0, my x1, my x2, etc. And if I take some y, which is an A tilde, remember A tilde is a subset of A prime, and A prime consists of elements of the almost disjoint family other than x0, x1, x2, etc. So this y will only hit each of these in at most one point. It may fail to hit some of them in any point at all, but it will only meet them in one point. And so now suppose the y looks exactly like this. How do I build a z in here that does not hit that y at all? Well, you just have to make sure that it grows fast enough. Right, so first I will, let's say suppose that 0 wasn't good W0. Let's take 0 and put into Z. So we put 0 into Z. So now this is what I've drawn here. Oh, including this one. What I've drawn here is y. So y is this thing that hits each of the x0, x1, x2, and at most one point. So let's say we can put 0 instead. So 0 is an element of W0. And now I just need to make sure that I put something bigger than that one point in there. So I just make sure that, that one point. So I make sure that what I've called z hat of 1, make sure that z hat of 1 is greater than the min of y intersected with x0. And in general, I guess I want to make sure that z hat of n plus 1 is greater than the min, max, the max of y intersected with xn. Maybe I need to write this in the indices. Sorry? This looks x, thank you, xc hat n. And if I do this, I'm sorry this end of the proof didn't come out so well, but if I do this, the point is, reiterating this, the point is that this y, that allegedly I am supposed to hit infinitely, it only hits x0 in at most one point. It hits x1 in at most one point. So simply by choosing this z to grow fast enough and have big enough gaps, it will put some, if it puts anything into x0, you can choose it so that it's bigger than this thing. And then you move on over to whatever whatever set hat of 1 is over here, but what you're putting in, you can just make the gap to the next thing big enough so it's bigger than whatever y has in common with x z hat of 1 and so forth. And so now you're never going to hit this. And that's the end of the proof. And I'm way out of time, apparently. So apologies for the disorganized end to the talk. The paper exists in a draft that some of you have already received it by email. So if you want it, let me know. Thank you.